Hi to all. Now I am going to explain one important topic in magnetism, that is circular current loop act as a magnetic dipole. How circular current loop act as a magnetic dipole? Magnetic dipole means magnet. This current loop behaves like magnet, and one face of the loop, current loop, this is a wire. Okay, it is a wire wound, one turn, that is called as loop. Wire wound with many turns, it is called as coil. And this current carrying loop behaves like magnetic dipole. Magnetic dipole means bar magnet. Dipole, in magnet two poles are there, south and north, equal and opposite pole strengths. Okay, south and north, they are separated by certain distance, that is magnet, and that is only called as magnetic dipole. And now I am going to explain that the circular current carrying loop, okay, circular current carrying loop act as a magnetic dipole. This will act as magnet, and this current loop act as magnet means this is also should have some magnetic moment. That magnetic moment formula also I am going to derive. This is important topic, very important. Okay, this is very important. And now let us see. For that, this is a current loop. It carries current I. Okay, and from the circular current loop radius is capital R. From the center on the axis at a distance x, I want the magnetic induction. Magnetic induction on the axis of circular current carrying loop, that we know already. We discussed in the moving charge and magnetism chapter. This derivation will be there, and that is a Bad-Sawart law application. The formula for the B is mu naught Ni R square by 2 of R square plus x square whole power 3 by 2. This is the formula, we know already. Where n is the number of turns, I is the current, R is the radius, x is the distance on the axis where you are finding the magnetic induction. This we know already. And here I am taking that if x is greater than capital R, then R is neglected. R is neglected. Okay, and when we neglect the R, this denominator term will be changes like this. When you compare with x, R can be neglected. Okay, not in the numerator, in the denominator, right? When R is very less, x is very high, no need to add this R to x. That means R can be neglected. Then the formula we will take is like this. Okay, R is neglected when compared with the x. Then this R square plus x square. Okay, that R square plus x square in sum we take like this. This is B is equal, we will get as mu naught Ni R square by 2 of this R we write as 0 square plus x square whole power 3 by 2. Now we have to simplify this some more. That is mu naught Ni R square by 2 into x square whole power 3 by 2. This 2 by 2 will cancel. You will get 2x cube. Okay, and little bit I will modify this one. Okay, how I will modify? Right, then let us see here. Magnetic induction on the axis of the coil I want to find out. Just I want to change like this. That is, I want to multiply with 2 pi and divide with 2 pi. Okay, and this is multiplied with 2 pi and divided with 2 pi. 2x cube. This is multiplied with 2 pi and divided with 2 pi. Then this we will write as mu naught by 2 into 2 pi we write as 4 pi into, this is 2, this remaining is Ni pi R square we write, just modification, by x cube. Okay, it was very simple step, you see. I multiplied this equation with 2 pi and divided with 2 pi, then there is no problem. And this nu naught I wrote, 2 into 2 pi I wrote 4 pi. Okay, here 2 is there, 2 I wrote, n I wrote, pi r square I wrote. Okay, but pi r square is what? Area, right? And this we write as like this. B is equal to mu naught by 4 pi into, this is 2 into NIA by x cube. Why we write A? Because R is the radius of the coil. Pi r square is the area of coil. Pi r square equal to area. Okay, right. This we take it as equation 1. Okay, and now magnetic induction on the axis of dipole. Magnetic induction on the axis of magnetic dipole. What is the formula for that? Okay, and what is this? This is a magnetic dipole. This is the south pole and this is the north pole. And now from the center, this is the line passing to the two poles. This is called as axial line or axis of the magnet. From the center at a distance x, I want the magnetic induction. This is the magnetic induction on the axial line of the bar magnet. This we not derived. This is similar to the electric field intensity, right? I gave the table in the part previous lecture. From that we write the formula for the B. Okay, that formula is mu naught by 4 pi into, in case of short dipole we write as 2m by x cube. We know that one already. This is equation 2. This is in case of short dipole. Okay, short dipole. And now from equation 1 and 2 we write one thing, right? What do we write from equation 1 and 2? Two are similar, right? This is the current, magnetic induction due to current loop and magnetic induction due to bar magnet. Both are similar, right? Nu naught by 4 pi, nu naught by 4 pi 2, right? X cube, everything is same, but instead of capital M here NIA is there. That means from equation 1 and 2 we write, from equation 1 and equation 2 I will write one thing. What I will write? From equation 1 and equation 2 we write one thing, that current loop behaves like magnetic dipole. Magnetic dipole or magnet. Okay, right. Current loop act as a magnet or magnetic dipole. When compare the equation 1 and 2, okay, we can compare the equation 1 and 2. When current loop act as magnet, okay, magnet has the magnetic moment, then the current loop also has the magnetic moment. You can compare equation 1 and 2, then the magnetic moment of this coil you will get. Generally bar magnet has the magnetic moment, but now the current loop also have the magnetic moment. Completely it will act as a magnet. Okay, now let us compare equation 1 and 2. Compare equation 1 and 2, and then after that we can write the magnetic moment equation. Nu naught by 4 pi, nu naught by 4 pi is there, x cube is there, 2 is there, m instead of magnetic moment for the bar magnet, magnetic moment is there. For the current loop NIA is there. That means current loop magnetic moment m is equal to NIA. The magnetic moment of current loop formula is NIA, where n is the number of turns, I is the current and A is the area of the coil or the loop. Okay, right. Let us see, and now you take the screenshot. Okay, now you take the screenshot, and then after that I will rub it and I will continue. Within 2 steps it will be complete. Now let us continue. Right, within 2 steps this topic will complete, and that is I am going to compare the equation 1 and equation 2. Compare equation 1 and equation 2. Then magnetic moment of coil, circular current carrying coil, yes, that is you compare u naught by 4 pi u naught by 4 pi 2 x cube, then NIA is there, right? This is the formula for the magnetic moment. This is very important formula. This is equation 3. What is N here? Number of turns. N is the number of turns. I is the current in the coil. Current in the coil. Current carrying coil behaves like magnet. This is already completed. I will wrap totally. A is the pi r square, right? This is area of coil, where small r is radius of coil. If the coil is in circle shape, we take the pi r square. Okay, otherwise we cannot write pi r square. Other rectangle, if it is rectangle, we write LB. And here, in case of current loop, magnetic moment of current loop I want. Magnetic moment of current carrying loop. Current loop. Yes, current loop means it has only one turn. Remember, coil means many turns, loop means one turn. Then N is 1. If N is 1, then what you will get? Then magnetic moment you will get is only IA. Right? This is the formula for the magnetic moment of current loop. Right? Magnetic moment of current loop. This is completed. Okay? Thank you for watching my lectures. Subscribe my channel and share to your friends.